Good afternoon, everyone. I know the session post-lunch is quite difficult, but thank you for bearing with us. The topic for today is carbon capture and separation. I know carbon capture sits at the sort of base of industrial decarbonization, looking at chemical engineering and the applications thereof. We have an eminent list of panelists today to help talk you through some of the technology challenges, the engineering challenges, and of course, the cost challenges, right? So we look forward to a very engaging session. Our first speaker for today is Mr. Vinay Parab from Worley, and he's going to be talking to us about engineering excellence and how to optimize costs. Vinay, over to you.
Thank you for the introduction. So, in today's topic, I will try to bring together our experience of building several carbon capture plants from the engineering perspectives. So, there are lots of opportunities available to reduce the cost of carbon capture. So, let's see what's the different opportunities available there. So carbon capture is an important tool that has to decarbonize the industry, but there are several challenges. The cost of CO2 capture, the CO per ton of CO2 is still high, and then we need to do the engineering excellence to bring down the cost of CO2 capture. First of all, the engineering firms, they are play a vital role to identify the cost saving opportunities. It starts from the concept phase, feasibility, moving to FEED, and into detail engineering and the construction phase. In the concept phase itself, it starts from the identifying the technology which is suitable for carbon capture for the particular industry in question, and then moving towards then shortlisting the licensor who can help us in the capturing the CO2. Then the process scheme of complete carbon capture has to be jotted down in the concept phase, moving towards the integration strategies, layout, and the constructability. The constructability is very important to start from the beginning so that we can have a good planning and keeping the end in mind. So at the end of concept or feasibility, what you can get as an output is the process scheme freeze that can be used for the FEED phase and the cost estimation of class 3 or class 4. That forms a good base for the FEED phase, and in FEED phase, based on the flow scheme that we have decided, it actually move into the detail engineering of the flow schemes, equipment sizing get decided, and we get the good foundation in terms of cost. So this is the phase wherein we take the final investment decisions, and the cost estimation of plus and minus 10% can be achieved at the end of FEED. Based on the FEED, next comes the detailed design and the procurement, wherein we started to actually engage with the vendors, start onboarding them and implement the vendors' input into the actual design and start with the construction phase. In construction, we have written the constructability, modularization and logistic planning. They are very important to bring the cost of the total capture down depending upon the constructive philosophy that we are adopting. So before moving forward, I just try to see, so my discussion I am trying to limit to the post-combustion carbon capture and essentially for the solvent-based absorption process. And it starts with the conditioning flue gas in quencher, then absorbing CO2 in the CO2 absorber column. And what you get at the stack is decarbonized flue gas. And the rich amine or the rich solvent can be regenerated in the regeneration, and subsequently its compression, dehydration and the liquefaction depending upon the end specification that we require. So the whole intent of showing this slide is you just keep in mind the block diagrams or the blocks involved in this so that you can correlate how we can reduce the cost of this capture scheme in the engineering part. So essentially I will take through the 6 points here, which will has a potential to reduce the capex and opex for the carbon capture plant. The first is heat integration, equipment selection and design, plant layout optimization, construction strategy, modularization strategies, and how AI tool can help us to reduce the cost of carbon capture. Heat integration. If you look at the CO2 capture from the absorption process, it is very energy intensive process, and we require a lot of steam in the regenerator or the desorber. Hence, every efforts which can be reduce the steam or which can help us to take a steam from our own plant is very useful. I just try to bring here three aspects. One is recovering heat from the flue gases. So extracting flue gas through through a economizer or heat exchanger could be one of the possibility which can reduce the steam demand for the capture plant. There is a concept called mechanical vapor recompression. The steam from the stripper can be recompressed and put it back into the system so that you can reduce the total steam demand for the capture plant. And the thirdly is CO2 compression utilization. When we compress CO2 from low pressure to very high pressure, that is a requirement for the end specifications, you actually dissipate lot of heat to the cooling system. This heat can be used to generate the steam and put it back to the regenerator. And this system has been implemented on one of the projects to capture CO2 at Norway. Then comes what are the equipment selection and design aspect that we can take care to reduce the cost of the carbon capture plant. So there are few critical aspects like starting from the flue gas duct, flue gas fan, the quencher, the absorber, the compressor package, dehydration and liquefaction. They are mainly the cost drivers and the schedule driver for the complete project. And the engineering experiences and the engineering optimizations can be performed to reduce the cost of the whole capture plant. Starting with the flue gas duct and the fan, if you are talking about capturing CO2 from the industry to a capacity of 1 million, 1.2 million, the duct size that you can think of is in a range of 5 meter to 6 meter in dimensions. For such a huge flue gas duct, there is an optimization possible in terms of reducing the diameter of the flue gas duct, but it has a penalty of increasing the pressure drop and hence the power requirement of flue gas fan. Hence the cost effectiveness of flue gas duct versus the power requirement has to be carried out using the CFD analysis and using the VFD for the fan. Quencher and absorber. For the large scale plant, the absorber can be more than 10 meters. And when we are designing such a large absorbers and quencher columns, there has to be an optimization study performed. There are two aspects. One is the construction material. It can be constructed in terms of steel or concrete, or it can be a cross section of circular or rectangular. So the site specific study is required to arrive at which absorber column is best suited and cost effective for the site in question. Compressor package. What you get out of capture plant is low pressure CO2 stream. It has to be compressed to very high pressure CO2. And for that there are two types of compressor available, integrally geared and inline compressor. Again, the choice between choosing this compressor is depend on the capacity that we are talking about. A good discussion and interaction with the compressor vendor is here required to come to a solution of which one is the better for the capacity that we are talking about. And then the flow scheme and the selection of cooling media. The cooling media here can be air, water or sea water, but which one is best for the site that we are talking about has to be analyzed at the early phase of the project. Dehydration package. So depending upon the CO2 specification at end of the battle limit, we need to choose between the different dehydration possibilities. It can be using glycol absorption, membrane separation or emulsive. The emulsive gives a very low levels of moisture at the end of capture streams. Then comes a liquefaction package. Again, there are two sets of packages available. One is a self-refrigeration and another is the external refrigeration. So depending on the capture capacity that we are talking about, we need to choose which one is best for the capture capacity in questions. So in a way, there are lots of options available starting from capturing CO2 from the flue gas till the end specification. But which one is best suited is to be done by the capex and opex analysis or throughout the life cycle of the project, and it has to be done at the early phase of the project. Then comes the plant layout. Generally, the carbon capture plants has a good characteristic that it can be implemented in and retrofitted in the existing plant, but it then comes with the challenges of layout and fitting the carbon capture plant into the existing facility. It's very economical to have the absorber near to the emitting point, but always it's a challenge to put that absorber near to the capture plant. Hence, we need to keep that absorber at a remote location. But there are some pros and cons with that. If you have to keep the absorber away from the emitting point, then It avoids interfaces with the process stream. It avoids a major modification, but then it increases the duct length and hence the capex of the plant and hence the opex of the plant. So what could be the best option, or the another option that we can think of here is a split unit configuration, wherein the flue gas fan, the quencher and the absorber can be kept near to the emitting point, and the rest of the facility can be kept away from the capture point. So it helps to reduce the duct length, reduce the pressure drop on the fan power, and gives a better operation control. But at the same time, because of long solvent length transfer lines and high pumping cost, it has to be a cost analysis done before we choose which one is better, and depending on the layout that we have it from the existing facility. Construction strategy, as I mentioned at the beginning also, that it has to be a construction-led engineering. That means we have to keep the end in mind at the beginning, how we are going to construct the plant, whether it is a modular or the stick built, and accordingly the test work packages has to be made, and we have to back calculate it, which packages we have to start early, and it can be further divided into engineering work packages and procurement work packages. It decides the complete schedule, and then you will get the right equipment at right time at the site and reduce the whole construction cost for the project. In modularization, again, the modularization gives a lot of advantage, because then it's reduced field work and improved safety, but then it comes with the cost. If you have to transport whole modularization plant from the remote area, it associated with a lot of cost with the transportation. So in modularization, the prefabricated unit can be bring to the site and reduce the amount of efforts that we require at the site. When you are thinking about capturing CO2 at small scale, say in a range of 100,000 to 200,000 tons per year as compared to 1,000,000 tons per year, then there are licensor available which provides the modular plants, and it's best suited for the brownfield applications. Stick built, for the large scale plant, the stick built is gives the good result, because then we can bring the prefabricated equipment pieces at the site and do a less work at site, but then a complete modularization for the large scale plant is not possible, and there has to be a study performed versus what can be modularized and what can be a stick built, which gives essentially a good idea and reduce the cost. Again, AI tools, there was a session here before that AI can be used to reduce the carbon capture plant. So yes, the answer is yes. It's possible in simulation and modeling. There AI can help to reduce the cost. Rapid optimization, there could be several evaluation that we have to perform during the design of the carbon capture plant, and that is possible with the AI, wherein we can do a evaluation of multiple options in a quick way. Predictive maintenance is possible with AI, and real-time optimization. So these are the tools that are available to reduce the cost of CO2 capture. So in summary, I will say that there is a lot of experience with the engineering firms while designing the several carbon capture plant that can be used. The learnings from the different carbon capture plants can be used to reduce down the cost for the future projects, and for which a good collaboration between the capture licensor, the engineering firm, and the owner itself is required to bring this cost to the level down. With this, I conclude this session, and I try to just bring the experience of designing several carbon capture plant ranging from the small scale to big scale here. It's a summary of what can be done here, but there is lot of optimization is required behind it, right from the concept phase until the construction phase of the project. Thank you.
Our next speaker, Guillaume Rodrigues, I hope I'm pronouncing that correctly, heads the carbon capture product line, and he's going to be talking to us about their innovative solutions in this space. Over to you.
Hello everyone. The purpose of this presentation is to share about a technology that is CryoCap. The purpose is to explain how this technology is positioned versus other technologies, to explain a bit how it works, and to share about the market momentum of the technology. Yeah. And in a nutshell, before talking about the technology, maybe a few words about Air Liquide. For those who may not know the company, So this is a global company that is installed in present in more than 60 countries with 66,000 employees and with a 27 billion euro revenue. Air Liquide is selling some gas, so that's a selling gas company, and we are managing essential molecules. The most famous one are the air molecules, oxygen, nitrogen, argon, but we are also producing and selling hydrogen, helium, CO, and many others. And another key molecule for today is the CO2. Air Liquide has a historical and large market for the CO2 food grade with an installed capacity for liquefaction and purification of CO2 that goes above 10,000 tons per day today. Air Liquide is selling gas, but also developing technologies. And to develop technologies, we do it through a partnership between our R&D centers that you see here on the map and ENC. So I'm part of ENC. ENC stands for Engineering and Construction, and that's the EPC arm of Air Liquide. Now let's jump into the technologies, and to talk about technology, that's good to go back to fundamentals and to talk about energy. Maybe some of you know this curve, and this curve shows in the vertical axis the minimum theoretical energy that is needed to separate the CO2, and the horizontal axis is the mole fraction CO2. So basically, reading 0.2 here means 20% CO2 in a flue gas. So what this curve tells us is that there is an inflection point around 10 to 15%. Below this value, it will require a lot of energy to capture the CO2, and the low-hanging fruit of the capture is consequently above this value. And you can also see that the decrease of energy in the 15% plus range is linear with CO2 concentration. And last word on it, there is not a single technology that can mimic this curve. To be able to partly represent it, we need at least 4 technologies. So, having said that the CO2 concentration is the main driver for the cost of capture, here you can see a mapping of technology to capture the CO2 in flue gas depending on CO2 concentration. And the way to understand and read this graph is that below 15%, typically a mine wash is the most optimized solution to capture the CO2. Nevertheless, a mine wash requires a lot of it, a lot of energy. Intrinsically, it needs this energy to desorb the CO2 from the solvent. The other thing to say on a mine wash is that being a chemical absorption technology, this is poorly sensitive to CO2 concentration, so that finding CO2 sources with higher CO2 concentration does not bring much in terms of energy for the capture of CO2. Looking at the other side of the graph, above 95% CO2, the state-of-the-art technology, the other state-of-the-art technology is pure cryogenics. So it consumes something like 10 times less energy than a mine wash. Of course, it's not the same inlet CO2 concentration. And this technology is really adapted to concentrated sources because below 95%, the recovery of cryogenics will drop significantly. So that 20 years ago, when we started developing cryocap technology, between the two state-of-the-art technologies, a mine wash and the pure cryogenic, there were no really optimized technology that could capture the benefit of a given CO2 concentration. So what we have done is that we have combined our in-house technologies. We have kept the core cryogenics that we have combined either with adsorption, pressure swing adsorption, or with membranes. And now we need to go back to CryoCap FG. So on the left part of the graph, this is a technology that with the sweet spot start at 15% CO2, and that goes up to 50% CO2. And the basic concept is to first pre-concentrate the CO2 with a PSA, and then finalize the purification with cryogenics. Why do we need the pre-concentration? Simply because, again, as I mentioned, if the CO2 concentration inlet of cryogenic is not high enough, the recovery is not good enough. When the CO2 concentration is above 50%, so typically what we can obtain as a CO2 concentration through oxy-combustion, in this case we can enter directly into the cryogenics, but it will still lose some CO2, so that we use some membranes to recover the CO2 lost by cryogenics. And if we go back to this theoretical slide, with CryoCap FG, Oxy, and LQ, we can simply mimic the linear decrease of the energy depending on the CO2 concentration. Now going to the CryoCap is a range of products, a family of products. So I've talked about CryoCap FG, CryoCap Oxy, LQ, but we have as well a CryoCap H2 that is adapted to hydrogen production. I will come back to it. What are the main features of the technology? The first one is that it's using only electricity, and it can obviously be paired with renewable energy to avoid having any indirect CO2 emission. That's also a flexible design, and I will explain that. From the technology, we can produce the CO2 in the state we wish, gaseous, dense phase, or liquid with the same setup. And finally, and a very important criteria, especially for hard-to-abate sector, is that the technology only compresses and expands the feed gas. So there is no chemical, no flammable product that is used in the technology. Something I forgot to mention, maybe to come back to the efficiency there, is that just to give a sense of the efficiency of the technology, if we look at 20% CO2 concentration, a man wash will require typically 900 kilowatt-hour per ton of CO2 for capture and liquefaction. CryoCap FG will need less than 400 kilowatt-hour per ton. So really, when the CO2 concentration is high enough, it brings a lot in terms of overall energy consumption. First disclaimer, a bit sorry about some formatting going from Google to Microsoft that I discover here. I'll explain a bit how CryoCap FG works. So CryoCap FG is first a pre-concentrator that you see there, that is the CO2 PSA, and then a cold process. But before entering the CO2 pre-concentrator, we need to manage the flue gas. Flue gas is hot, contains some SOx, contains some dust, contains also some other impurities. So we quench the gas, we scrub SO2, and we remove the dust to a low level. We do that to be compatible with the following CO2 compression steps. So we compress CO2, flue gas below 10 bar, and we dry it deeply with high absorption dryers. So just inlet of the CO2 PSA, the flue gas is dry under pressure. The CO2 PSA absorbs the CO2. And then when the PSA is regenerated, low pressure but concentrated CO2 is generated. So that basically, if the flue gas is at 20% CO2, downstream the PSA, the flue gas is at 60%. This 60% CO2 is recompressed, typically above 20 bar, and enters the cold section. In the cold section, the temperature is lowered to below minus 50 degrees C, and here only CO2 liquefies. So that's really the way we separate the CO2 in the cryo section, is that we liquefy only CO2. Then there is some inlet gas of the cryo process that is not CO2, so that's nitrogen, oxygen mainly, and some CO2 because that's partial condensation. And so this stream containing the CO2 lost by cold process is recycled to the inlet of the PSA, so that the PSA further absorbs the CO2 lost by cryo. Now, we have just followed the CO2 path, but if we go back to the inlet of the PSA, we have compressed all the flue gas, that is mainly nitrogen, and this nitrogen is not absorbed in the PSA. So outlet of the PSA and the top of the PSA, that's pressurized dry nitrogen. And we simply recover this energy, the pressurized nitrogen, in expanding the nitrogen. We expand it in a wheel, in a turbine, that generates some mechanical energy that is used to drive the compression upstream the cold process. One important thing to say is that the recovery can go up to 98%, so we can really reach very high CO2 recovery, and we remove most of the NOx that are present in the flue gas while capturing the CO2. So the NOx present in the flue gas then are concentrated in the condensates of the system. This is an overview of the technology. Just one word to say that, yeah, that's a very large cryocap FG. So we have 2 trains of PSA, you see on the top corner. For smaller units, we have 1 train, and that's a major part in terms of footprint on the technology. Now going to cryocap oxy. So you've understood that cryocap FG is adapted to 15 to 50% CO2 concentration, and the first step of cryocap FG is a pre-concentrator. When the CO2, the flue gas itself, is already pre-concentrated, for example, through oxy combustion, we don't need this PSA anymore. So that we still manage the flue gas, we quench, we remove dust, we compress, we dry, and we enter the cold process. The cold process, we still lose some CO2, but here we don't have the PSA to recover the CO2 lost by cryogenics. That's why we add some membranes, you see, the vent gas permeation, that is simply a CO2 recovery system. Yeah, just one word about the cryocap H2. When producing hydrogen through natural gas, there is always or most often already an hydrogen PSA at the end of the process that is there to purify the hydrogen to very high purity. And in fact, this hydrogen purification system is a CO2 pre-concentrator, so that in the steam methane reformer, there is a source of CO2 with 50 to 70% CO2 low pressure. And basically, a cryocap H2 is like a cryocap oxy. That's compression, cold section, membranes. And the main benefit of this technology is that while capturing CO2, we are recovering all the hydrogen that is lost by the SMR, which really gives a credit in terms of CO2 capture cost. Just 2 words about cryocap LQ. LQ stands for liquefier. It has been mentioned in the previous presentation. There are 2 options to liquefy the CO2. External refrigeration cycle, basically compressing the CO2 up to 20 bar, liquefying with ammonia, for example, so that there are 2 machines. There is a chemical product or flammable product. Cryocap LQ is a self-refrigerated technology where the CO2 is compressed to high pressure, a pressure that is high enough so that the CO2 is liquefied with cooling water. So basically, at the CO2 densification part that you see there, the CO2 can be at 60 bar and liquefied with cooling water. But we want to produce the CO2 cold, minus 30 degrees C, 15 bar, for example, so that we need to subcool the liquid to minus 30 degrees C before expanding the pressure to avoid any flash. And that's really the concept of the cryocap LQ. And this cold that we need to subcool is generated through taking a part of the produced CO2 and expanding it to then recycle it to the machine. So that in this process, we have only 1 machine instead of 2, we have only CO2. So we have a less expensive, more compact, and HSE-friendly technology. I said previously that we can produce the CO2 in whatever state we wish. So intrinsically, the cryocap produces the CO2 gaseous under pressure, 10 bar or more. So that's the minimum we can do, I would say. When we want to produce the CO2 liquid, we need to add some cold to the system. So we have a machine that takes some CO2 from the process, compress and expand it to generate some additional cold. And overall, with the same setup, or very similar setup, we can go to low pressure CO2 5 bar, 7 bar, sorry, minus 50 degrees C, especially for Japanese or Eastern Asia project, or gaseous for aggregation hubs. Yeah, just one word to say that by default, the technology is modularized, so all the main equipment are delivered on skid. One word also about the sensitivity to the scale effect. Here, this curve, especially if you follow the blue line, it gives you the absolute capex depending on the size of the plant, the CO2 capacity. That's normalized to 1, so 500 tons per day, the capex is 1. And you see how stiffly the specific capex in euro per ton of CO2 decreases with the size. So meaning that the main project that you will see in the market momentum slide are at large scale, typically above 1,000 tons per day. This is about the technology. So the technology have been developed more than 20 years ago. We started developing the technology through validating each individual brick on different matrix, steel application, flue gas application, on coal, and different type of matrix. And then we have installed our first cryocap 10 years ago in Normandy. So that's in continuous operation. You see 300 tons per day. Then we have installed a very large CO2 PSA for ArcelorMittal in Ghent, in Belgium, that has started more than 2 years ago. And we have 4 cryocap under construction. One with Total Energy in France, in Grandpuits. The plant is ready to start. One in Netherlands, in Porthos, on a steam methane reformer. And you see the scale up, 6 times larger. And more recently, this year, we've been awarded to supply very large CO2 liquefier, 3,500 tons per day in the Nordics. So the project has started up something like 1 year ago. Just one word also about the capitalization. So Air Liquide is not only selling technologies, Air Liquide is operating plants. So we have this chance of being able to develop technologies and to improve technology through capitalization of our own plants. And that's the case of Port Jérôme, the plant with 10 years operation. So after 10 years, that's very successful operation with no aging of equipments, with very low requirement for maintenance. So it has been the basis for improvement of the other cryocaps. Sorry, and the main market today for CCS is in Europe because there are many drivers there. One of the drivers is the CO2 tax. That's a bit below 100 euro per ton, whereas the cost of the CCS chain in Europe is close to 200 euro per ton. So today, to have a chance to have a business case, to have a decision of investment, you need subsidies, a fairly high amount of subsidies. And the trick to have some project materializing is to be successful in getting the subsidies. And there is a main mechanism in Europe called Innovation Fund, where this technology got a lot of success. You see on the left part the project awarded based on cryocap, on cement, on lime, and the other side that's based on other type of application. Just one figure to keep in mind, cryocap represents more than 50% of the awarded project. So that's from far the most successful technology today in Europe for the CCS. And last slide to extend a bit the topic. So we've just discussed about the capture and the liquefaction, but Air Liquide is present in other areas. CCS is a value chain, so we are present in the capture, in the inland transport, in the large liquefiers, but as well on the liquid CO2 transport. We have a joint venture called OCEOS that is ready to launch the construction of the first ships for CO2 transportation overseas. And it helps a lot on the project to have all those bricks to manage the interfaces that are a key topic here. Thank you.
Our next speaker, Deep Shah, is going to be talking to us about how industries are going to use this. Over to you, Deep.
Hi, good afternoon, everyone. Thank you for joining. I know it's post-lunch, so it's not that the best time of the day, but thank you for being here. I'll do my best to keep it a little less technical, a little more engaging, more addressable to the wider audience. My topic today is helping industries meet CCTS targets. CCTS here represents Carbon Credit Trading Scheme. And we are trying to develop a practical guide which serves as a solution for any and every industry that becomes a part of the CCTS program. There are 3 broad questions that I'm trying to address today. First is understanding how targets are set under the CCTS model. Second, how do obligated entities, by that I mean the industries that are mandated under this program, how can they plan to meet their targets? And number 3 is sort of how do we scale up this solution and enhance it is accessible to everyone who needs it out there. Going to the first part, just setting some baseline. India has pledged that we'll reduce the GHG emission intensity, which is a short form for which is GEI, by 45% under the Paris Agreement. And CCTS is one of the many tools that we have developed to help achieve these targets. CCTS is basically a market-based mechanism where industries can help achieve this goal by reducing their emissions. India CCTS basically has two parts. One is the compliance market, and one is the compliance market, and one is the voluntary market. The compliance market is for obligated entities, which means large industries who are mandated to reduce some emissions. And the voluntary market is for anyone and everyone who is reducing emissions and can be a part of the market. Under CCTS, there are 8 sectors under the compliance market, and across these 8 sectors are 743 obligated entities or plants that are sort of assigned targets to reduce their GHG emissions. Under this model, each of these 743 entities are assigned a target. If they meet their target and reduce emissions beyond that, they are given some certificates. And someone who is not able to meet their targets, they have to buy some certificates, and which is why it is a market-based mechanism. One certificate here represents 1 ton of CO2 emissions, 1 ton of CO2 emissions reduced or removed. On average, I'll use my pointer here. On average, if we see each entity is assigned a target somewhere between 2% to 4%. These targets are based on a baseline value of 2023-24, and the targets have been assigned for the 25-26 cycle and the 26-27 cycle. You will see here there is a lot of variability in sort of what the emission reduction targets are. And again, we'll dive deeper into what these variability means, but the purpose for this slide is to explain what is the magnitude of targets that have been assigned and how they differ across entities. We now go on to how does an entity plan out to meet their targets, and there are 3 broad considerations that they have to use. One is what is the baseline and what is the target. By that we mean what's the starting point and where do they have to reach. The second is, in order to achieve that reduction, what are the different abatement options that are available. By this we means either management technologies or reporting technologies or investments which can help reduce the emissions. And the third is defining a pathway which will help them meet this reduction at the lowest possible cost. The core thing to understand here is this is not a one-size-fit-all exercise. Each entity under each sector will have to plan their own journey. And what is core to planning this journey is something called a MAC curve, or a marginal abatement cost curve. And we'll understand it a little better in this slide. This is what a curve looks like. On the x-axis is how much emissions can be reduced. On the y-axis is what is the cost of reducing that emission. And each bar here represents different strategies. And we'll go into detail, but I want to explain the fundamentals of what a MAC curve is. The purpose of this curve is to map what technologies are there to reduce emissions, what is the cost of that technology, and how much emissions can it reduce. You will see that there are some bars which are lower on the x-axis, which means there's a negative cost. A simple example here is deploying a rooftop solar or a ground mount solar. Effectively, solar pays for itself, so it does not have any additional cost. But then there are some other technologies which require some capex and opex investment, which means it has a positive cost. We take one sort of sample MAC curve for a cement sector. You will see that on the x-axis are different strategies that can be used to reduce emissions for a cement plant. The bottom here shows on the leftmost you start with a GEI of 0.66, which means that 0.66 tons of emission per ton of cement production. And if you implement all of these technologies or solutions, you can effectively go to as low as 0.01 tons of emissions per ton of production. Right. How to use this curve? So I've taken two entity examples. These are real targets based on what has been assigned by BEE. We have not named the entity, but let's take it as entity A and entity B. You will see that entity A has a baseline GEI of 0.61, and it has to go down to 0.6 by year 1 and go down to 0.59 by year 2. Similarly, entity B has a baseline of 0.42. It has to go down to 0.41 and has to go down to 0.40. These are actual numbers, just that the plant name has been anonymized. Now, if I am a part of any of these two entities, how would I think about how to meet the targets? I'll first map the baseline and my target GEI on the map curve. I'll then find out what my strategies are which can help fill that gap. From that selected list, I'll first try to prioritize any strategies that have a negative or a lower cost. And then if they are all sort of deployed, I'll move on to the higher cost strategies. And then because this is a market-based mechanism, which means entities, if you cannot reduce your emissions, you have the opportunity to buy certificates from the market, which means that if your strategies to reduce emissions are very cost intensive, you can choose to not implement them, but rather buy certificates from the market. And we'll try to implement both these case studies on the MAC curve. So we are taking a look at entity A here, which has to go down from 0.61 to 0.59. And you will note that on the MAC curve, they sit somewhere in this portion, between this 0.66 and between this 0.53. So naturally, there are all of these strategies that they can implement. It's an easy solution for entity A because all of these are negative cost. They don't effective net, they don't have to pay anything. The strategy would be to go from left to right and start deploying one solution at a time and stop the moment they get to 0.59, which is their target. If you go to entity B sits somewhere different on that MAC curve. They're sitting somewhere here where they have to go down from 0.42 to 0.40, which means all of these solutions on these left are ideally deployed, which is why they are sitting at 0.42. But if not, that is the priority. Let's say they have deployed everything, then the strategy should be sort of TSR or renewable electricity or things like that. Let's say these are all done, then they move on to looking at carbon capture and storage and moving on to carbon capture and utilization. The point to note here is that all of these are cost positive solutions, which means there is a financial decision to be made where is it viable to deploy a solution like this, or is it more viable to go to the market and buy a certificate from someone else who has done it. All right, so we thus far have established that sort of targets are very individual, which means each entity has its own target. There are 700 plus entities who have to meet this, but the approach to defining a pathway to meet this target, it fundamentally sits inside of a MAC curve. Whilst what I have shown you is a very sample theoretical exercise, but we see value in scaling this up and sort of finding partners from the industry side, from the government side, from the academic side to help build this into a model that is workable for all of these 743 entities across all of the 8 sectors. Just some key numbers. So across these 743 entities, they emit about 758 million tons. So we're looking at a large bunch of emission that is expected to be reduced as part of the CCTS. Again, as I said, the objective here is to present more of a prototype that can be scaled up. But the prototype is very practical. It is designed to help meet industries and not designed to be an academic exercise. I think it this will become much more valuable when there is real world data. It will also become more practical when we can link the actual costs of deploying these solutions with sort of the actual market rates for CCTS. This is just an ideation, but what this could eventually scale up is a digital, say a solution or a SaaS platform or a tool where entity A can come in, they can plot their starting points and their end points. They can map what all solutions are available. They can map that to which of these solutions have they already deployed, which of them have to be deployed. The digital tool also tells them what is the cost, the net cost for deploying these solutions, and how will each of these solutions help them meet their target. The visualization again here is centric, keeps a MAC curve at the center because it combines cost and technologies and GHG reduction, all three into one picture. I represent ICF Consulting, which is a consulting company. We have helped sort of at the national level, we are helping governments setting up the CCTS policy, setting up these baseline. We are also on the other end of the spectrum helping industries meet these sort of targets. Today, I think the core purpose of this presentation is number one, to explain how one can use a MAC curve to develop a pathway to decarbonization, but to also sort of keep out a call to everyone in this room and beyond, whether you are an obligated entity who is required to reduce emissions, if you are governments or you are donor agencies or climate finance institutions who may be looking to develop such solutions, or if you are a research think tank or technical organizations who we can partner with and we can help develop these solutions together. We're happy to get in touch with any and every one of these three buckets and sort of take this from a prototype into a workable solution that is accessible by industries in India. That's it. Thank you.
Thank you, Deep, for that. Our next speaker is going to be talking about direct air capture, which is one of those up-and-coming technologies which has own fair share of challenges. So, Anindya, over to you.
Thank you for this kind introduction. Today, I am planning to take you through sorbent-based direct air capture, and would like to give an overview of what Vernova is looking into right now. First of all, I must say this is not my work alone. There are 50 plus engineers who are burning their midnight oils to get to crack this difficult problem to address direct air capture. Definitely, it requires no further introduction why we are talking about carbon capture. If we need to meet the Paris Agreement target, we definitely meet a net zero all over the world by 2050. Before we go even to carbon capture, if we need to get to the net zero, let's understand where this carbon comes from. The carbon comes from because we are burning some way or other the hydrocarbon fuel. The pathways to reduce that emission is pretty simple to say, but very difficult to achieve. There are three ways. Don't burn fuel. As simple as that. Go for renewable, go for nuclear, go for energy storage, hydro. Or the other option is, if you really need to burn fuel, burn something which doesn't have carbon. Again, all these are very easy to say, but very difficult to implement and exercise at an industrial scale. We are all aware of that. But if we can go to some fuel, let's say hydrogen, ammonia, or a biofuel which is carbon neutral in a cyclic way, definitely that can reduce emission. And the last option, if we can't avoid any of these two, we must burn fuel, then we have to capture that emission to get to the net zero. There are ways to capture when you have a flue gas. You can capture 90, 95%, people are talking about 97. But nonetheless, even if you capture 97%, you are still emitting certain 2-3% out in the atmosphere, especially for hard to abate sector like cement, steel, or now data center is coming up where you have distributed CO2 source. There are only other option then to capture that net amount of CO2 from the ambient to offset the total emission, and that's where the direct air capture becomes valuable. If you look into the carbon capture in general, the process as it stands today, you need a material which has a certain affinity to CO2 and it can capture CO2. So you need a very efficient material which can efficiently capture CO2. People are talking about various materials in this space. Some are talking about chemical, liquid solvent. We are working towards the solid solvent material. Some are talking about pressure-driven membrane-based technologies. Once you captured it, it's done, then you have to release that CO2 in a controlled manner so that you can either sequester or utilize it for further valuation of that CO2. So releasing CO2 is the energy intensive process where all the challenges comes from. If you look into liquid, currently whatever system we look into, they regenerate around 600 to 900 degrees centigrade depending on what solvent they are using. If you are looking at solvent, which we are right now working on, that plays somewhere around 90 to 200 degrees centigrade. Or if you can go for membrane, that requires ambient. That goes by the material. Next it comes that how much energy you require to get that CO2 out. And that's where the energy requirement, and that becomes the challenge in the industry. And the last part is how efficiently you are managing that energy, you are reducing your loss, you are making the process more reversible so that you can do it at a minimized cost and energy consumption, so that you can do it at scale, at cost, and at a commercially viable manner. We are all familiar with PCC, which is post-combustion carbon capture. For a natural gas combined cycle, the flue gas contains 4 to 6% by mole of CO2. But if you look into the DAC space, which is 0.04%, which is 1,000th of probably the leanest flue gas that we can see today. If you go to coal or if you go to cement, they are much higher CO2 concentration. Higher CO2 concentration make it easier to capture. As you go lean and lean, it becomes more and more challenging, more difficult to do it at scale and in an energy efficient way. So the system that we are looking at is building itself is some kind of modular system where you can capture CO2 from a 400 ppm air, ingesting that, while it goes out at 200 ppm or even less, and that CO2 you want to capture in a controlled manner for further sequestration. There are already some players who were there for 15 plus years, some are new entrants. This is a very highly populated space. I would say some of the technology leaders I have already highlighted, but they are not the only one who are playing. There are many players in this space, and everyone is trying to crack this code to capture CO2 from the ambient. The two different part of this is, as you probably looked into the previous solution, some are looking into the liquid solvent like carbon engineering, and many are looking into the solid sorbent, which is Heirloom or Climeworks or ours for that matter. A liquid solvent is nothing but where you dissolve the CO2 in a liquid, and then usual agent is potassium hydroxide or calcium hydroxide. You form a calcium carbonate, you heat it up and you regenerate that agent again for further capture, and you separate the CO2. While in a solid solvent, it's some powder which has a certain affinity to CO2. A little bit to distinguish about solvent and sorbent. Solvent is where you get the CO2 dissolved into a liquid, whereas sorbent is a more surface phenomena, either by the pore size where it physically goes inside it and sits in the molecular pores, which is physisorption, or we try to go to a chemical process so that some chemical bonding happens, which is more efficient, especially in a scenario where you have CO2 at a very sparse amount. You need much efficient collection of CO2. A chemical affinity works much better. So there are always some amine groups or some other chemical agent which helps in improving the CO2 affinity. Once you crack the material, then it becomes important, how do you ensure that CO2 comes in close contact with that material? So there you need to provide equipment, either a reactor or we call it a contactor, through which you can make an efficient connect between CO2 and you can make an efficient mass and heat transfer. There are few options as I highlighted here: fixed bed, moving bed, or fluidized bed. Each has its own challenges. Fixed beds are good. Moving bed are even better to control the cycle time when it's rotating, but very difficult to engineering, design it when rotating and the stationary object comes as an interface and you need to do sealing and so on. Fluidized base, on the other hand, has issues with the solvent stability in the long run. Now, when I was talking about that sorbent where CO2 comes, it has an affinity to capture CO2. What you need in an ideal sorbent is that it should have a great affinity of CO2. More the CO2 it captures, it's always better. So per kg of sorbent, how much CO2 capture is very important. At the same time, not just a high affinity is good enough, you want it to be very fast. You don't want to wait for hours before it gets saturated with CO2. Although it captures a lot, but it's a very slow process. You want to capture a lot of CO2 in a very fast process so that you can have an industrial application out of it. So we can combine the capacity and what we call the rate of capture is the kinetics together to call it a productivity. Once you have a great sorbent which is a very high productivity, then you have efficient system can be designed out of it. In our lab in Vernova, the researchers are researching on designing these sorbents. At the crux of it is those amine groups which can help in bond with CO2 to have a great high capacity and high productivity. We work on that designing those and testing that in a powder form in a thermodynamics and kinetics evaluation. Data analytics helps us to design and down select the sorbent. Once those are done, sorbent and film properties are established. We put it through a rig where actually air can blow on top of it, and you understand these properties when air is blowing it. It's not a stationary condition. So we go for different stages of designing the sorbent and testing and down selecting, which makes commercial viability. I'd like finally when you sorbent and it connected with amine, linker and metal, you need to provide a contactor. For us, the contactor is some modular design which can be easily scaled up by adding a number of such modules to go to a different scale, be it 50,000 ton per year to 250,000 or 1 million ton per year, to design a plant out of it. I have a slide to provide the details of it. So this is what a module would look like. During the operation, it will open up its valves, air will come, it will contain CO2, which will get in touch with the sorbent to get absorbed. Inside it, it lies what we call a contactor. It's basically a plate and tube heat exchanger. The plates are coated with some sorbent, that the coating that we are designing. Once it gets saturated with all the CO2, then you heat it up by sending hot water through the pipes of it. It starts heating up the sorbent and release the CO2 when everything is sealed, and it requires certain amount of vacuum. That CO2 then comes out and you can capture that and you can compress it to the right pressure for sequestration or storage purpose or further usage for pipeline delivery. The hot water heats it up. Once the process is over, you need to send the cold water through it so that the temperature of the contactor comes down again and it gets opened up for the next process of adsorption or CO2 capture. That's the way we are envisioning of the system. You can multiply it with the numbers to get a plant out of it where number of contactors can operate in sync or in a certain fashion or certain synchronization to give the right amount of capture throughout the year. So as I was highlighting, the efficiency of the whole process lies at the trifecta of these three things: a good sorbent, a system where your energy release is much more efficient or the amount of energy required is much efficient, and then you need a plant design where all your systems works efficiently. We have right now, we have done already sorbent design, we have worked on the contactor design, we have developed a small lab scale demo by 23-24 timeline. At this point, we are looking like a commercial piloting. We are looking for some installation, commercial installation in Canada to prove it at scale, at a smaller scale for the time being. For 29-30 plus, we are looking at a large scale commercial operation where our target is to capture CO2 at $300 per ton. Maybe eventually our target is to make it even lower, less than $150 per ton. Whereas if you look into the PCC, that space target is to capture CO2 at around $70 per ton, eventually going down to $40 per ton. That's where the Vernova is committed towards the CO2 capture and making the net zero emission possible all over the world. Thank you very much.
Thank you, Anindya, for that. I think cracking the DSC puzzle will be key to sort of enabling adoption. Our last speaker for today is Rajarshi Panigrahi, who is going to be talking to us about innovations that PSUs like OIL are doing in this sector.
Good afternoon to all of you. Today's topic is hybrid graphene aerogel platform for sustainable carbon capture. So this is a collaborative project between All India and IIT Jodhpur. So today's the content will be introduction and motivation behind taking this study. Then the development of hybrid material for CO2 capture, as well as the involvement of this material as photocatalyst, and then the summary that whatever the challenges we have overcome and the innovations and impact we have achieved. So the human activities release more CO2 than can be absorbed by the natural process. So this leads to increase in CO2 in the atmosphere, and so as per this latest data by US government, the concentration of carbon dioxide in the atmosphere is exceeding 420 ppm. So the activities like fossil fuel combustion for energy production and cement production, these are the main contributor of CO2 pollution. So this leads to these activities leads to trapping of CO2 in the atmosphere and thereby rising the temperature. So we need to trap those CO2 in the atmosphere so that the concentration of CO2 can be minimized. There are certain CO2 capture technologies available, like amine scrubbing. So this is using an amine based solvent for CO2 capture, but it has some limitations like to solvent degradation, etc. And the nanoporous adsorbent are also being used, and it is being utilized in Europe, China and US. And the algae based captures are also there, that is utilizing the microalgae based capture technology using natural photosynthesis, but the process is very slow. So our project overview is that we are aiming to convert the waste biomass to wealth. So we have taken biomass like cactus or water hyacinth to convert those waste material to a value-added product, and to synthesize the material that is capable of absorbing CO2 and as well as it is acting as a photocatalyst for CO2 reduction to green fuels, C1, C2 fuels. And this material is also regenerative in nature just by simple heating at 60 degrees centigrade. So graphene aerogel is a class of 3D porous nanostructure carbon material with tunable porosity, and it has a very high surface area. But the challenges are there for synthesizing this kind of material, as it involves multi-step synthesis, requirement of very high temperature, often requires more than 1000 degrees centigrade, and the need of supercritical drying. So, and commercially available graphene aerogel is costing more than 25,000 to 45,000 rupees per gram. So we have taken one alternative approach for synthesis of graphene aerogel from cactus by doing the low temperature pyrolysis around 300 to 400 degrees centigrade. And this material has been characterized through FESM, TEM, etc. So the hybrid graphene aerogel, that is 2D MOS2 3D graphene aerogel, has been synthesized from graphene oxide and ammonium molybdenum sulfide by doing the self-assembly method for 10 days, followed by the freeze drying. So we to at this to level we have obtained MOS2 graphene aerogel hybrid material, and this material is so robust. So I can so I'm showing one video So in this balance, we are putting coin over the material, and it is supporting, and the mechanical robustness is still there, and it can support 1129 times its own weight. So this proves that this material is very robust in nature. So the carbon dioxide capacity, the absorption capacity of the material is measured through gravimetric method, and it has been observed that it can absorb 500 to 600 milligram per gram with an efficiency of 85 to 90%, and it has a very low energy demand. It involves room temperature process, but compared to other available CO2 capture technologies like geolites, the absorption capacity is 100 to 300 milligram per gram. But the amine scrubbing method, it is very efficient, and it is capable of absorbing CO2 at 7 kg of to CO2 per liter of amine solution. But the regeneration process of the commercially available technologies are very harsh, as the geolites are requiring more than 100 degree to regenerate the material. It is our technology is very cost effective, because our starting material is from waste material, and this particular material is capable of absorbing, as well as it has the capability of converting CO2 to C1, C2 fuels. So, but the other such technologies, they are only capable of absorbing CO2. As we have discussed, that this material is also capable of producing hydrogen from water, and it has been observed that in 1:1 ratio of molybdenum sulfide and graphene aerogel, it is giving maximum gas evolution rate. So it is. So we have fixed the ratio of molybdenum sulfide and graphene aerogel at 1:1, and we have observed that under the sunlight, it is giving maximum gas evolution rate, that is 1.2 millimole per gram per hour of hydrogen under normal sunlight. I have a video to show that demo. So this particular material is capable of converting CO2 to methanol, and then the production of methanol is characterized through HPLC and NMR. So this, based on our laboratory study, we have observed that this material is very cost effective, and we can accomplish 3 steps in a single process, like waste management, mitigation of greenhouse gas, and production of green fuels. And this material is very selective for CO2 capture. This is highly recyclable, more than 50 cycles, and we have observed that the capacity is maintained over 95%. And due to this 3D morphology, it is very easy to handle. The challenge is like the cost, but the cost thing we have overcome, that the overall process cost as well as the material cost is very less. Second is the infrastructure. There is no much need of any additional infrastructure, or there is a minimum modification of the existing infrastructure is required. Then transportation that absorb CO2 can be on-site converted to C1, C2 fuels there itself. So there is no need to transport the CO2 to another place. And the scalability, that across the energy sector, this technology has a strong potential for So for scalability, because of the multifunctional nature of the hybrid material. So we have developed this innovative material from waste biomass. The multifunctional nature of this material serves both as an absorbent for CO2 capture and as a photocatalyst for CO2 reduction to C1, C2 fuels. The estimated production cost is around 1000 rupees per gram, which is very less than the commercially available product, that is around 25,000 to 45,000 per gram. And this this entire process is designed to mimic the natural photosynthesis for catalytic reduction to catalytic reduction of CO2 in presence of water. And the proposed technology can cater to various market segments, like for carbon capture, for producing green fuels, for using graphene aerosol in another purposes like energy storage, water purification, etc. And the energy input cost is very less compared to the other existing technologies, and it is completely a room temperature process. Thank you. Thanks a lot.
A big thank you to all the panelists and to the audience for being patient listeners. Thank you very much.